Okay, now what we'll look at is interference of sound waves. What this means is we'll look at several sound waves reaching a point and seeing what is the effect. Okay, so here are two speakers. And what this diagram is showing you is, so this speaker is emitting waves, and these are crests, and the white circles are troughs. Okay, so that's a crest and that's a trough. And so this speaker is emitting wave, so is this speaker. And you see, at this location, at this point, a crest arrived from one of the from that speaker, and a crest arrived from this speaker. Okay, so two crests arrive at the same location and they constructively interfere. So the amplitude is twice as large, and the intensity is 4 times as much, as 4 times as if a single speaker was playing. So at that level, that's constructive interference. At this location, so that's purely constructive, two crests. At this location, two troughs reached, and that's also purely constructive. Okay. And again, that will sound 4 times as loud as, I mean, the intensity will be 4 times as great as from a single speaker. Now, on the other hand, in these black spots, you see a crest is reaching from this speaker and a trough is reaching from the other speaker. So this is happening. A crest from one speaker reaches and a trough from another speaker reaches, and they cancel each other. Okay. Okay, so at that location, you would get no sound. Okay. So this is destructive interference, and then so various locations have have constructive and destructive interference. That's for this particular frequency. So if you had two speakers in a concert hall, this seat wouldn't hear those frequencies. Okay. And so you wouldn't want to put seats there. Okay, so an audio engineer has to figure all that out. Okay, so for instance, let's okay, so here are two speakers, and I'll show you with speaker separation. So all these dark spots are destructive interference for this particular frequency. Okay, so you have to, oops. Okay. And depending on speaker separation, and this is the phase difference is 0. Oops, playing frequency, this is, okay. Anyway, so depending on different frequencies, you have locations for the destructive interference. All right, so how do we figure out where is constructive interference and where is destructive interference? Okay, so let's say you're interested in this path. The wave traveled this distance from that speaker and this distance from this speaker. Okay. Delta R is the path difference. And it turns out that the path difference is an integer number times lambda. So there was speaker 1, speaker 2, that's the location you're interested in. That's the distance traveled from speaker 1, that's the distance traveled from speaker 2. And L2 minus L1 is delta R. And if the path difference is n lambda, then that will be a constructive interference. And if the path difference is a half integer times lambda, then that will be a destructive interference. Okay. And for other distances, it will be an intermediate situation. Okay. So for instance, if the path difference is lambda, an integer number times lambda, you'll have constructive interference. And if it's half integer lambda, you'll have destructive interference. Okay. So this is the condition for interference. Okay. So here's a device you can use. So a sound wave splits into these two paths. And as you move this armature, you can make this sound wave travel larger and smaller distances. And as you move this back and forth, you'll hear constructive and destructive interference. So the sound intensity will go from 0 to loud and back and so on, so on. All right, you guys might own noise cancellation speakers. So this has been made possible because of cheap and small electronics, miniature electronics. So if you're listening to music which is being fed through there, and you don't want to hear any sound, any of the noise coming from outside, you just want to hear your music. All right, so the way it works is outside sound is sampled here. It's sent to a processing unit. So this is the processing unit. All it does is it takes a wave and inverts the wave. So there is the original wave, outside noise coming in, and this processor has produced an opposite wave. And so the produced wave and the outside wave cancel. So that's how come all outside noise is canceled and you just listen to your music, okay? And this works best for lower frequencies. So those noise cancellation speakers will not work for hard rock stuff. Okay, sound localization is the fact that how do you tell where the sound is coming from? Okay, so how do we know where the sound is coming from? You have 2 years, and so that's how you can localize sound. So for instance, if humans were born with just 1 year, we wouldn't be able to localize sounds. And just like that, if you were born with only one eye, you would not have depth perception, and so on. So the head shadow, the most distant year sound attenuation is most effective for higher frequencies. So for higher frequencies, so let's say something, a sound is on your right, and this is your right ear, you hear the sound, and for the left ear, that sound has to go through your head. And that's how you know that the sound is to your right. Okay. So the intensity, the loudness at the left ear is lower than the intensity at the right ear, and that's how you know. Okay. For lower frequencies, the arrival time difference between the 2 ears is the main clue to localization. Okay, so let me. So for higher frequencies, this is your right ear, left ear, a sound wave. For higher frequencies, this intensity is lower, and so that's how you tell. And for lower frequencies, when the frequency is lower, the wavelength is higher. So let's say a wavelength, the sound wave whose wavelength is greater than your head's wavelength. Okay, you'll have to rely on time difference, because not even one wave passes through your head and not much attenuation happens. So it's the time difference that you have to rely on. For very low frequencies, sound cannot be localized. And so for instance, let's say the sound frequency is 100 hertz, the wavelength is 3 point. So speed of sound is frequency times wavelength. Speed of sound is about 340 meters per second, and a frequency of 100 hertz, the wavelength would be about 3.4 meters. And that's a large wavelength. So, and it turns out that you cannot localize a sound to a location smaller than the wavelength. So this is roughly the size of localization. So for low frequency sounds, you can't tell the speaker, the location of the speaker within, let's say, three to 5 meters. Okay? And that's 3 to 5 meters. That's as wide as that table in the lecture hall that we use. Okay, so that's quite a large distance. So for very low frequencies, sound cannot be localized. So that's why your home theater system only has one subwoofer. The subwoofer plays low frequencies, and you can place the subwoofer anywhere because you can't locate it anywhere. And for higher frequencies, you can locate where the sound is coming from. And so stereo, so you have to have several speakers. All right, now we'll talk about the Doppler effect. Okay, so here is a source that's producing sound, and here is a fellow who's sensing the sound. Okay. Now these circles represent the crests that are produced. So if this source is producing a 100 hertz frequency sound, the pitch is 100 hertz, it's producing 100 crests a second. And if this guy is stationary, 100 crests a second will pass him, and so he'll hear a frequency of 100 hertz. But on the other hand, if he's moving towards the source, more than 100 crests will pass him, and he'll hear a pitch that's greater than 100 hertz. If he's moving away, less than 100 hertz crests will pass him a second, and he'll hear less than 100 hertz. Okay, so let's look at this simulation. Okay, so here we go. So here's a source that's producing sound, and you see if the source is moving in this direction and you're standing here, you'll hear a higher pitch. If you're standing here, you'll hear a lower pitch, and that's the Doppler effect. So when the perceived pitch is different than the emitted pitch, you hear, that's the Doppler effect. Here's a source moving at the speed of sound, and you see all the crests are collecting here, and that's a shock wave. Here is a source moving faster than the speed of sound, and all the crests will collect on the surface of a cone, and that's a shock wave. So this is Mach 1 moving at the speed of sound. This is Mach 1.4 moving supersonic, moving faster than the speed of sound. So when observers and source move relative to each other, the apparent frequency is higher than the emitted frequency. So if the observer and source move toward each other, then the perceived frequency is higher than the emitted frequency. So this formula gives you, this is the perceived frequency, this is the emitted frequency. V is the speed of sound, V0 is the speed of the observer, Vs is the speed of the source. And sign convention is observer and source velocity are positive when they move toward each other. Okay, so this would be positive if the observer moves towards the source, and this would be positive if the source moves towards the observer. And they would be negative otherwise. Okay, so let's look at the formula. Okay, so here's the source, here's the observer. Okay. And here's the perceived frequency, here's the speed of sound, observer speed minus source speed, and emitted frequency. So let's say observer is moving at 10 meters per second, okay, and source is moving away at 5 meters per second. Okay. And the source emits a frequency, this is the emitted. Okay. So F prime would be V, the speed of sound is 340 meters per second, 340 or 343. And the formula would be 340. The observer is moving toward the source, so that would be positive. So that's plus 10 meters per second. 340. And the source is moving away from the observer. So his velocity is negative, negative of negative. So that's plus 5 meters per second. Okay, so that would be the, so this would be the perceived frequency, that would be the emitted frequency. Okay, so that's how that formula works. Okay, and anyway, it covers all cases. So again, the Doppler effect is the perceived frequency is different than the emitted frequency because of the relative motion of the source and the observer. Okay. Now bats use echolocation. So that's how they see, and they use frequencies higher than 20,000 hertz. Okay, and so here's how they see it. So things, here's how they see things. They'll emit a chirp, and the chirp is reflected back. So from the time delay, they know how far this object is. From the intensity of the reflection, it knows how big the object is. And if the object is moving toward the bat, then the reflected frequency will be higher. And so from the frequency difference, it knows the relative motion of the object. So the bats use time delay, intensity of reflection, and frequency shifts to sense their environment. Okay. So here's a shock wave. A shock wave is produced when a source moves faster than the wave. So for instance, here is a source. When the source was here, it produced a sound wave. And a little while later, the source has moved there. And the sound, this wave, sound wave has only traveled there. So you see the source has gone out of that circle. And when the source moves faster than the speed of sound, see, all the crests will collect on a cone. And that's on the surface of a cone. And that's a shock wave. And so that's a high pressure area. Okay. And so there's a lot of energy on the envelope. And this angle, the shock angle, is given by sine theta, is given by V is the speed of sound, and Vs is the speed of the source. Okay, so this equation has sine theta can be only less than 1. So this equation has a solution when the speed of the source is greater than the speed of sound. Okay, so here's a bullet traveling, and there's a shock wave. Okay. Now, you see shock waves when boats go by as well, because the speed of surface in shallow water, the surface wave travel fairly slowly, and a boat easily can travel faster than those waves. So you see a shock wave on when boats are going on a river as well. So a plane, flying plane, will generate 2 shock waves, one from the tail and one from the nose cone. And when the shock wave goes by you, you hear the boom. So this guy has heard both the booms. This guy has heard only this boom, hasn't heard this boom yet, and this guy has not heard any booms yet. Okay. Now, it turns out that this the nose cone produces a pressure spike. So let's okay. So let's go here. So here is the pressure. So the nose cone pressure. So this is atmospheric pressure. It produces a positive pressure spike, and the tail produces a negative pressure spike. So this is a high pressure. This is a low pressure. Okay. And whenever you have low pressure, of course, air would expand and so on. So if you decrease the pressure, it would expand, the air would expand. And if there's any moisture present in the air, expanding air, the temperature would decrease, and any moisture present would condense into a cloud. So If you decrease the pressure around the parcel of air, this air would expand and any moisture there would condense. So let me show you a phenomenon. Okay, so. All right, so I don't know if you guys have seen this a video like this. Yeah. So this is at an air show, and they show, so this is a plane flying faster than the speed of sound. And you see all that moisture condensing near the shock wave of the tail. Okay? Because of the low pressure, the air there expands and you see the moisture condensing. All right. So those are the shock waves. All right. So now we'll look at musical instruments. Here are stringed instruments. You saw that you can only excite standing waves, so you can only excite certain frequencies. This is the fundamental frequency for this string. This is the first or second harmonic, depending on how what different people use different terminology. So, and this is the, I like to call it the third harmonic, second harmonic, and so on. Okay. Okay, so the modes of vibration of a string fixed at both ends are given by this equation. Okay, n is the number of antinodes, so n is 1 for this, n is 2 there, n is 3. T is the tension in the string, mu is the mass per unit length of the string, and L is the length of the string. Okay, so the way you play different frequencies in a guitar is you have 6 different strings to choose from. Those have different mu values, and for each string you can change the length of the string. Okay, so by using a combination of these two, you can produce different frequencies. The tension, of course, in the string has to be set before you start playing the instrument. And all integer values are allowed. Okay, so guitar is a pretty versatile instrument. You can produce a whole bunch of frequencies. Yeah. Here is a flute, for instance, an instrument which has pipes open at both ends. So the frequencies you can produce, again, for a pipe open at both ends, you have antinodes at the ends. Okay. And all the frequencies are allowed, except that in a flute, you cannot change the length too much. You change the length by covering various holes and a combination of holes. So you can't change length as well as in a guitar string. Here's an instrument where the pipe is closed at one end, and this instrument can only produce the odd harmonics. So L is the length of the pipe and so on. So this instrument is, a closed pipe is not as versatile. So in a harmonica, for instance, for a given pipe, you can only produce a certain frequencies. So what you do is you compensate by giving more tubes. So in a harmonica, there are many more tubes. Okay. All right. Here is a drum head, and I believe I've shown you this before, but let's look at this simulation again. Okay. So this is how a drum head vibrates, and if you hit at different locations of the drum head, you set up different vibrations. So that's how a drum head vibrates. Okay. We'll quickly talk about beats. If you produce 2 sounds simultaneously whose frequencies are close by, so this is So you will hear an intensity. The sound will, its intensity will go up and down with the beat frequency. Okay, so, and the beat frequency is just the difference in the two frequencies. So you might have seen musicians tune their instruments. They'll use the tuning fork, they'll sound the tuning fork, and then they'll play the instrument. And if the instrument is slightly, if the instrument frequency does not match the tuning fork frequency, you'll hear a sound whose intensity goes up and down as per the beat frequency. Okay. The timbre of the sound. So here is the same note being played by three different instruments. And when we say a note, what we mean is the period of the wave is the same. Okay. Of course, the shape of the wave is different, but the period of the wave is the same. So here is, let's say, a tuning fork playing the C note, the flute playing the C note, and the clarinet playing the C note. Okay. So what's different is the harmonic mixture. Okay. So here's the tuning fork. The tuning fork is a pure tone. The flute has this harmonic mixture, and the clarinet has this harmonic mixture. The clarinet has higher proportion of the higher harmonics, so it'll sound tinier. Okay. And the harmonic mixture is what's called a timbre. So that's the timbre of the sound. That's the quality of the sound. Okay. And so it's for the harmonic mixture that different violins are differently priced. Okay. Now, the musical tone was given to us in the Western musical tone was given by, is the one that's currently used as the one given by Bach. And between A's on the piano, so the middle A is 440 hertz, and the first higher octave is 880 hertz. And then there are 11 half tones between them. Okay. So 440 times 2 is 880. And between them is 11 half tones, each half tone being higher by 1.06 hertz. So 1.06 times, by a factor of 1.06 times. So each half tone, the frequency increases by 6%. That's what that means. Okay. So these are the various frequency ranges for various singers. Sopranos have the highest pitch, altos, and the fundamental frequencies in that range, tenors in that range, baritone in that range, and so on. All right, that finishes this chapter. So I will stop recording. I will